Hello everyone. After a little break, we are resuming our quantum chemistry course. So today we will start our fourth chapter, and this is lecture 16. So here today we are going to discuss the postulates of quantum mechanics. So we will only talk about few very basic fundamental postulates in as simple manner as possible. So these postulates are basically almost like axioms of geometry. Okay, so they are very fundamental. So based on those postulates, the rest of the quantum mechanics or quantum chemistry would be developed. So now you may wonder that why we are starting from the fundamental postulates right now, because to understand the basic or the fundamental postulates, we need to have some little background knowledge of quantum physics or quantum chemistry. And it took almost 15 lectures to come to a position where we believe that now we can understand some few basic principles about quantum mechanics. Okay, so that's why we started this postulates of quantum mechanics, supposed to be the very first chapter. We are starting it a little late. Okay, so let's focus on that. So firstly, once again, I don't think I need to mention it once again, that these postulates are for quantum mechanics. So that means this is only applied on the particles that follow quantum mechanics. So the question is, what kind of particles that don't follow quantum mechanics? So basically the macroscopic body don't follow quantum mechanics, and we have learned that the atomic and subatomic particle follows quantum mechanics. And how to differentiate between the two in a more scientific manner? So we can easily say, so the particles for which we can precisely and simultaneously determine position and momentum both, those are not following classical mechanics, those follow classical physics. Doesn't follow quantum mechanics, those follow classical physics. And for the particles for which we are unable to precisely determine position and momentum simultaneously, those follow quantum mechanics. Okay, so now here we once again come back. So we will talk about our first postulate. So we will call it the postulate number 1. Okay, so basically the postulate number 1 says that the wave function of a particular particle or a system actually contains enough information to describe the system or the particle completely. So in other words, the postulate 1 says the state of a quantum mechanical system, okay, can be defined by its wave function itself. So I have written psi, the wave function, within bracket r and t. So what is r and t? Definitely we are describing position by the letter r, and of course time by the letter t. So by these two parameters, the position and the time, with these two we can basically define the entire quantum mechanical system. Alright, so a little bit more in continuation of the postulate 1. So we can also write 2 sentences. So that means what? So that means that also if we do like this, psi star rt multiplied by psi rt, so that means the wave function multiplied by with its complex conjugate, all right, and multiplied by the volume element. Okay, so I am taking dx, dy, dz as if the system is dependent on 3 dimensions. So instead of dx, we have all these 3 dx, dy, dz, and together this is called volume element. So this thing is actually denotes the probability. Okay, so probability of finding the particle within the volume element, that is dx, dy, dz. And of course we knew that this part itself, psi star psi, or we can take the modulus of psi whole square, is known as the probability density. Okay, so this is basically the postulate number 1. So once again, the state of quantum mechanical system is defined by psi rt, where r is position and t is time, and psi star psi dx dy dz defines the probability of finding the particle within this particular volume element. So now let's quickly take a look what are some important corollaries or some important obvious conclusion comes out from this postulate 1. So let's quickly take a look here. So the outcomes of the postulate 1 obviously says that if we take this probability density psi star psi rt, and then with the volume element dx, dy, dz, alright. So if I want to integrate that, means if I want to find the total probability, so we have already had some prior knowledge that the total probability of a well-defined quantum mechanical particle or system should be equal to the 1. That means the probability should be 100%. So this should always be equal to 1 provided the total integral in all 3 dimensions. Okay, so that means here we can take x, y, and z. So for all 3, from minus infinity to plus infinity, if we take this total integral, this should be equal to 1. Okay, so this kind of integral is called as a triple integral, because so far we had been working on only 1 dimension, that is x. So now these are 3-dimensional systems. So we have dx, dy, dz. So we have to deal with some triple integral. All right. So, or in other words, we can replace this triple integral like this to make a shorter form. So plus infinity to minus infinity to plus infinity, integral psi star rt psi rt d tau. Okay, so the tau is called the volume element, so this should be 1. All right. So from my previous lectures, you can readily tell me that at which condition this entire integration should be equal to 1. So it can only happen if and only if the psi star or psi are normalized. Okay, so you have to take a normalized wave function, then only this should be equal to 1. All right. So obviously now there are some important corollaries. Okay. So side by side we can conclude that if this is to be true, then these psi rt should be triply integrable. Okay, so that means we can write that psi rt should be triply integrable. I am not sure whether this is a very correct or good English, but what I mean to say that psi rt should should be able to be integrated within minus infinity to plus infinity along all three axes, means x, y, and z. So that's why it's called that it should be triply integrable. All right, or it's better instead of triply integrable. Okay, I think we can use a better term. Okay, so the better term is called quadratically integrable. Okay, since it's a triply integrable, we can write the psi RT should be quadratically integrable. So the question is, what some more informations or some more conditions to be fulfilled so that my psi RT should be quadratically integrable. Alright, so here again we are continuing with our corollaries. So that means we write that for psi RT to be quadratically integrable, we have to make sure that they are fulfilling certain conditions. Okay, and what are those conditions? The conditions is number one, that is psi RT must be, all right, finite within the above limit. So here what is the limit? So here the limit is minus infinity to plus infinity. Okay, so whatever the limit, it could be minus infinity to plus infinity, minus a to plus a, depending on the system, or 0 to infinity, whatever. The psi RT within this limit must be finite. And not only that, within this limit, the psi RT must be single valued, okay, and continuous. Okay, all right, but this is not all. So for being quadratically integrable, there is also a second condition that must have to be fulfilled. What is the second condition? The second condition says that not only psi, but the first derivative, okay, with respect to x, y, or z, whatever, the first derivative of psi RT, okay, must also be. So again, those three conditions: finite, single valued, and continuous. And within which limit? So within the same limit that we are talking about here. So for this particular case, we are talking about minus infinity to plus infinity. But if the system is applied to something else, like from minus a to plus a or 0 to infinity, that particular limit should be applied on that. Alright, so I hope now I am a little bit clear to you in explaining the postulate number 1. Alright, so let's take some very small examples to check our understanding whether we have understood the last two conditions of postulate 1, because these two are very important conditions. So I will frame a few questions for you to check our understanding. Okay, so let's do that. Okay, so before we just go to test our knowledge, let's finally understand one thing, that is, whenever psi RT fulfills the last two important conditions, that is, it should be finite, continuous, and its first derivative should be finite and continuous, etc. If the psi RT follows all that altogether, then in conclusion we call it that psi RT must be well behaved. Okay, so to define everything for a quantum mechanical system, its corresponding wave function must be a well behaved one. So therefore, as a bit of exercise, let's try our understanding whether all these given functions can be regarded as a well behaved one. So for example, the first one, e to the power minus x, verify it's whether whether it behaves well between 0 and infinity. So behaves well means these the earlier two conditions, that is whether psi t means the function itself is finite, single valued and continuous, and its first derivative is finite, single valued and continuous within the given limit, that is 0 to infinity in this case. So for the next one, e to the power minus x minus infinity to plus infinity. For this one, sine n pi x by a minus infinity to plus infinity, sine inverse x minus 1 to plus 1, sine x divided by x 0 to infinity, and then e to the power x minus infinity to plus infinity, and separately you do it for 0 and r. So you can take r as any arbitrary constant, and then the number 8, 6. Okay, so this is number 6 and this is number 7, sorry. So in number 7, e to the power minus modulus of x and minus infinity to plus infinity. So therefore it's your job to try yourself and see whether you get a conclusive, whether you can reach a conclusion whether the given systems are well-behaved functions one by one. Alright, so that's all about postulate 1, and now let's move on to the postulate number 2, which is the most simplest postulates you will ever find in quantum mechanics. So let's try to understand that. So the postulate number 2 says that any physically measurable property or a physically observable quantity that you come across associated with a particle in classical physics, there corresponds a quantum mechanical operator for that property in quantum mechanics. Okay, so for example, I have made a heading of title of a table. So now I am going to fill up the table one by one. So what do I mean to say? So one of the observable in classical physics is position. Okay. So the symbol of positions, it can be either you can represent it either by x or r, and the corresponding symbol of the operator may be x cap or r cap, and the operation is basically the multiplication. Okay, so I'm just writing multiplication. So that means you have to multiply something with x or something by r. So that's the meaning of it. And then after position, we can have momentum. Okay, so momentum is a physically observable quantity. All right. So for every observable in classical physics, so we can measure quantum, we can measure momentum of a particle in classical physics. So correspondingly, an operator. Okay, so the momentum we can define it by p. So for one dimension, we can call it px, and the operator, of course, you have seen it, px cap. So a momentum operator too does exist in quantum mechanics, and this momentum operation is nothing but minus I h cross del x or d dx. Okay, so and then we have the kinetic energy. Kinetic energy is a physically observable quantity. So in its symbol, maybe we can write as kx here, and the operator we can take kx here, and the operation is minus h cross square divided by 2m and d2 dx2 or del 2 del x square. Alright, so like this we have potential energy. Alright, so the symbol is u. If it is a function of one dimension, then ux, and then ux cap is the operator. So the physically observable quantity potential energy symbol with ux, so there exists operator that is called the potential energy operator ux cap, and it is and its operation is basically the multiplication. Okay, I'm just writing multi here. and then we have the total energy. Okay, all right. So the total energy, the symbol is E, and symbol of the observable is E, and the symbol of the operator we already know that it is called the Hamiltonian operator for the total energy. So the total energy operator is Hamiltonian operator, and it is and its operation is basically kinetic energy plus the potential energy. So what we have to do here is we have to simply take this, that means minus h cross square divided by 2m d2 dx2 plus ux. Alright, so this should be the total Hamiltonian operator, total energy operator for the physically observable quantity energy. So, and for example, we can write another quantity which is new here, and we have not talked about this before. It is angular momentum, and its symbol is Lx. Alright, and it is defined as y multiplied by pz minus z multiplied by py, and its symbol is Lx cap. Alright, and its operation, so I am just writing here minus IH cross and then y del del z minus z del del y. Alright, so this is the operation for the angular momentum. So why the angular momentum is being expressed by this kind of apparently weird formula with this kind of weird operation? We will definitely learn about that in the chapter of angular momentum sometime later. But for the time being, so I hope that there is no doubt about the postulate too. So these are the physically observable quantities, and correspondingly these are the quantum mechanical operators, and these are the bunch of operations. So the thing is that in order to measure or in order to find an information about the physically observable quantity like position or momentum or kinetic energy, we have to take the particular operator, that is momentum energy operator or kinetic energy operator, and we have to take the operator and we have to operate the corresponding wave function, and then after doing the operation, whatever the outcome is, we have to consider it. Okay, so whether this is if this is an eigenvalue equation is there, so the corresponding eigenvalue would straight away would give us the expected or the predicted value. That means whether it is energy or kinetic energy, whatever. Alright, so regarding that, we will be learning about our next postulate. So postulate number 3, which talks about eigenvalue and eigenequation. Alright, so let's take a look at the postulate number 3. So here we have the postulate number 3. So I would read out the postulate number 3 for you. So it says, if there's an observed value of any observable associated with any operator A, then the observed value is one of the eigenvalues. Alright, so what does it mean? So that means, suppose you just take a look at this the statement here, and then I'm trying to explain it to you this way. So if there is an observed value, so remember a free particle confined in a one-dimensional box. What was the observed value there? Means that you can actually predict and you can observe. The question is position? No, you cannot pinpoint a position. So your position in that case is not a accurately observed value. Same goes with the momentum. But energy, okay, the energy of the free particle in a one-dimensional box, it becomes a truly observed value. And so there was an operator associated with that energy, that means the Hamiltonian. So then the observed value, that means the energy values, become the eigenvalues. Okay, so is that clear now? So I am describing it in this way. So the statement, the postulate number 3, is basically nothing, but it says that if the operator A operates on psi, then we have the eigenvalue A multiplied by the wave function itself. So A psi is equal to A psi. Okay, so that's the whole meaning of it. Okay, but there are some few important stuff that we have to mention, we have to remember. Before that, once again I remind you that for a particularly one-dimensional box, the momentum operator P, if you take the momentum operator and operate with psi, you would never get an eigenvalue equation. So you won't get any eigenvalue. So that means for that particular system, momentum doesn't become an observed value. Okay, so that means it can be predicted by an eigenvalue equation. Same thing goes with the position of also. So the example energy suits well with this postulate number 3. Okay, so we can have some of the corollaries. Okay, so the corollary says that generally, and so the corollary says that generally an operator, okay, will have a set of eigenvalues. Okay, so what is the set of eigenvalues? So you just remember here that if A operates on psi n, then we'll have the eigenvalues A n psi n. Alright, so where I can write that A n stands for A1, A2, A3, etc. up to A infinity. Okay, so the set of the eigenvalues an. All right, so this is called the set of eigenvalues. Yeah, this is also denoted as the spectrum. This is just a terminology, the spectrum of the operator A. All right. So an example. So the example we can remember right here. So for a free particle in a one-dimensional box, we can take the Hamiltonian operator and operate with the psi, that is root over of 2 by a sine n pi x by a. All right. And then what we get? We get the energy value En, again root over of 2 by a sine n pi x by a. Alright, so this is my psi, so we can write like this: psi n is equal to En psi n. Alright, so where n is equal to 1, 2, 3, etc. up to infinity. So we can now tell that E1, E2, E3, E4, etc. all those eigenvalues form a set of eigenvalues. Okay, and those E1, E2, E3 values are dependent on the value of n, and those constitute the spectrum of the operator, the corresponding operators. In this case, those E values are the spectrum of the Hamiltonian operator. All right. So once again, we just since we are talking about this free particle in a one-dimensional box example, so as a corollary, we must emphasize on two important statements. So what are those? So let's take a look. So the two more things that I want to draw your attention into, that if we solve the values for energy for a free particle in a one-dimensional box, and you have already seen this equation. All right. So for any value for n is equal to 1, 2, 3, etc., we get discrete values of energy. So that means here the energy is quantized or discrete. So what condition gave us these discrete values? All right. And on what condition gives us or should give us a continuous energy values? So the answer was hidden within the boundary. Okay, that means within the limits. So for a free particle in one-dimensional box, remember the particle was confined between 0 to a or minus a to a. So that means those two boundary was. So that means although the particle was free to move within the boundary, but the particle is not free to move anywhere along the x direction. Okay, so that means the particle was a bound particle. So for this reason, I make two statements. The statement 1 says that for any bound system, or that means for any particle which is bound, in quantum mechanics the energy definitely it has to be discrete, and for any unbound system, alright, so for any unbound system, that means for a particle which is free to move anywhere from minus infinity to plus infinity in x direction, so what should be the energy? You are right. So energy is continuous. Okay, so these are the two corollaries comes side by one of these corollaries comes side by side from postulate number 3, and there is one more statement to make. All right, and let's clear out the whiteboard and write it freshly. Okay. So the second or the last statement in today's lecture is that, remember, postulate 1 does not say that a system must be in a state described by an eigenfunction. So what does postulate 1 say? The postulate 1 says that you need a well-behaved function to describe a state of a system. Okay, so if you have information about R and T, and if that psi is well behaved, so that psi can define the quantum mechanical state. But it does not say that to get the system defined, the system does not have to stay under the eigenvalue condition, or it should not only be described by an eigenfunction. So what then? So then the other part of the statement 2 is that any well-behaved, okay, suitable function can serve as a possible wave function of a system. Alright, so that means it's not necessarily the eigenfunction has only the right to define the system. Any well-behaved and suitable function that fulfills all the criteria, means the criteria of the becoming well-behaved and also the criteria that fulfills the boundary value conditions, okay, and all other conditions, can be taken as a possible wave function for the system. So you want an example? I can give you very quickly. For example, that the psi n, okay, for free particle in one-dimensional box, we have known like this. Okay, so this is a soft function, and we know that this function is an eigenfunction of the Hamiltonian operator. Okay, but the question is, I am asking another question: can this function psi is equal to, right, a multiplied by x minus a, alright, whether this function can be a possible whether this can be a possible wave function for a free particle in a one-dimensional, confined in a one-dimensional box. Alright, so we have to see whether this acts as a well-behaved suitable function and fulfills all the necessary criteria. Okay, so what are the necessary criteria? So for a free particle in one-dimensional box, as we have mentioned, so this is x is equal to here 0 and this is x is equal to a, and the condition was that psi at x is equal to 0 is 0, and psi at x is equal to a is 0. Alright, so if we put x is equal to 0, alright, so no, so possibly this is not the case then. If I get it like this, yes, then it becomes okay. So let's see, if we put psi at x is equal to 0, at x is equal to 0, it becomes a square. Alright, so we have some problem here. So anyway, we can come to that later. We will discuss these conditions later. So the point is, so can any other function psi, okay, can any other function define the state of a free particle in one-dimensional box? Okay, so that means, can any other function act as a well-behaved, suitable function that fulfills all the criteria for the system, but that is not the eigenfunction yet for the system? So basically the statement 2 says that the postulate 1 is not particularly made for an eigenfunction of a system. So any suitable well-behaved function fulfilling all the necessary criteria can define the state of a function. Okay, so my next example means in the next lecture I will come up with a different function for psi to show you that that kind of function also meets all the criteria to define a particle in a box, but still that is not the eigenfunction. Okay, so I hope you have some ideas now about the first two postulates. So you please read the postulate from the textbook, and we will meet again in the next lecture, lecture 17, and we'll discuss about some two more postulates, and we will particularly take up this issue in the next lecture. Okay, so till then, goodbye.